Continuing in linear approximation, 4.5, we're ready for number 3, I believe. Consider the equation y equals sine x at the point x equals pi over 3. It says we know, with a little thought, you would know the ordered pair corresponding to this angle is 1/2, comma, square root of 3 over 2. In other words, at pi over 3 on the unit circle, the ordered pair is 1/2, comma, square root of 3 over 2, because remember, ordered pairs are of the order cosine sine. So the cosine of pi over 3 is 1/2. The sine of pi over 3 is going to be square root of 3 over 2. Now, part A asks us, since the angle pi over 3 is approximately 1.04, so on and so forth, so in other words, if you do pi and divide it by 3, let's write the linear approximation for x equals 1.05. Okay, so first of all, remember that formula we were using yesterday, right? Where it was the f of x is approximately equal to L of x. And I'm trying to remember how we had it written. It was what? F prime of A times, I'm trying to remember without looking, x minus the x minus A, and then
I think it's plus.
Plus.
F of A plus F prime of A times x minus.
Well, that works.
Yeah.
Oh, they had the f of A out front, didn't they? Okay. I don't care which way you write it. Either, That's right. They did, yesterday they did have the f of A out front, and then the f prime of A times x minus A. Same idea. Okay, so with that in mind, okay, what is our A value we're using? Our A value is going to be that pi over 3. Okay, that's going to be our input value. And they're asking us to write the linear approximation from 1.05. So we'll sub in the 1.05 in the end. Now, with this in mind, well, do I really want to call pi over 3 our A value? Yeah, I do. I had to stop and think about what I want to, So with this in mind, okay, sorry. For our ordered pair, if it's pi over 3, what's the y value going to be? In other words, what is sine of pi over 3? And go back right here to our ordered pair.
Square root of 3 over 2.
Okay. Square root of 3 over 2, yes? So the ordered pair we're going to be using is pi over 3, comma, square root of 3 over 2. And then we also need our slope. How do we find the slope? We need the derivative, yes? So if y is sine, what is y prime? Cosine of x. And so we're going to evaluate that. We're going to be doing cosine of pi over 3, which is 1/2, according to our ordered pair, yes? And that is going to be our slope, or f prime of A, if you will. So let's go ahead and write our equation here. The f of x, which is approximately equal to L of x. And whichever you want to put first, so slope, 1/2 times x minus our A value, minus pi over 3, and then plus our y value, which was square root of 3 over 2. That's your equation. What did they ask us to find? X is 1.5. So they're asking us to find the linear approximation at 1.05. Now, you can stay fractions, you can go decimals. It's 1/2 in place of x, 1.05 minus pi over 3 plus square root of 3 over 2. And for obvious reasons, there is a calculator on this one, isn't there? Because we're not doing that one without a calculator. So you can plug that in. Yep. I would leave that in your calculator. And if you already took it out, then just arrow up and it's still there.
Oh, there's a part B.
Yeah, there is a part B. And I wasn't going to put this in my calculator, but then I decided to, which is why you're giving me a moment here. Okay. So we know the linear approximation is the 0.86742, nope, 4266282. Or minimum expectation, you have to have 3 decimal places, right? Now, B asks us to find the error of our approximation. We never actually did any error yesterday, I don't think. But if you flip back to where it talks about finding error, back on page 238, I guess it also talks about it on page 239. In order to find the error, you're doing the exact minus the approximation. Okay, and it's the absolute value of that. So, with that in mind, the exact would be, what was our original function? Our original function is sine of x here. Okay, so, which it gets a little confusing, but we're going to think of that as f of x. So we're doing the exact. So f of 1.5 minus our linear approximation of L of 1.05. Okay, so you do want to find on your calculator the sine of 1.05. And you're going to do the exact minus the approximation. No?
That's what I got.
So my calculator says negative 3.4026 e negative 6, which that's scientific notation, right? Okay. So that's the same thing as saying times 10 to the negative 6. So if I write this out without the scientific notation, 5 zeros, right? So that's what that error is there, okay? Now, with that in mind, if you go back there, it talks about in order to represent, let's see, find the error of your approximation. I don't have a clear final answer. So I think you can express it in a couple of different ways, but one of the ways it talks about expressing error on number 5 on page 239 is error is stated as being less than 10 to some power, 10 to some negative power, where p is the number of zeros in your result. And so one option, how many zeros are in this result? There are 5 here, right? So since there are 5 zeros there, that would be stated as the error. So absolute value of error is less than 10 to the negative 5th. Okay. That's one way to express it. Not to say that you might not need to just give the error as this also. The negative 3.4026 times 10 to the negative 6, because that is also your error. Okay? Okay. Questions there? Okay, let's try 4. Find a linear approximation to y equals 2 to the x at x equals 3. Use the tangent line then to estimate x equals 2.97. So in order to do our linear approximation, what do we need? Essentially, we need an equation that's going to consist of the point and the slope, yes? So if we're doing this at x equals 3, right? We're doing this at, so I'm going to say f of x equals to the x, so then what do we know about f of 3? That's going to be 8. So the ordered pair of 3, 8. What else do we need? Slope. So derivative of 2 to the x. What's our derivative rule for a to the x, basically?
Oh, yeah.
There is a natural log in there. Make sure I have it right in my brain, yeah.
Shoot. Natural log of 2.
Mm-hmm.
Times 2 to the x.
Uh-huh. So f of x equals a to the x. The rule is f prime of x is, I don't remember which way we did it, but what was it? Natural log of a times a to the x, or maybe we had it the other way around. A to the x times natural log of a. Something along those lines. So 2 to the x times natural log of 2. If we plug in, what are we plugging in? 3. 2 to the third times natural log of 2 means I'm going to have a slope of 8 natural log of 2. Okay, so write your equation. Find the linear approximation. What are you starting with? Slope, so 8 natural log of 2. X minus 3, and then plus 8. Okay, find a linear approximation. So there is the first piece when they ask you to find the linear approximation. Then it says what? Use the tangent line, so that's the tangent line, to estimate x equals 2.97. So you're doing linear approximation at 2.97. 8 natural log of 2 times 2.97 minus 3 plus 8. Yeah, there is definitely a calculator symbol there. Rightfully so. .834. I have written down 7.83364. Same equivalency, yes. Okay. Those my first 3 decimal places match up. So what I have this written as is therefore that f of 2.97 is approximately equal to the linear approximation of 2.97 which is that 7.834 that we just got. Okay. 5. Approximate 2.01 raised to the 5th power. Use your calculator to find the accuracy of the approximation. Is the linearization an overestimate or underestimate? And explain. So they're asking us to approximate 2.01 to the 5th. What's the base function here? In other words, because to write a linear linearization, we need, what's the original equation? What are they hinting at?
3y equals 2.01 x
Reverse that.
I'm just going to say 2.01.
2.01 is the number that's going to be changing. That's your decimal, because we're going to look at what's happening to what's close to 2.01 at 2. In other words, to write our linearization, we're going to write it at 2. So we're going to write this with the idea of our function being x to the 5th. Okay? Is that 2.01? That's your decimal. That's your clue that that's the variable that we need. Okay? So we're going to write the linearization of f of x equals x to the 5th at x equals 2. And then we'll find the linearization there. Okay? So, piece of information I need to know. Okay? We need a point and a slope. If we talk about a point, what is f of 2 going to be? Not one we know off the top of our heads. 2 to the 5th is 32. So there's going to be our point. Slope? Derivative is 5x to the 4th. And then we're going to need to know what f prime of 2 is, yes? F prime of 2 is 80. So we have a slope of 80, yes? Okay. So if we're writing our linearization, okay, which basically it's the tangent line, the slope of 80 times x minus 2, and then plus 32. Okay. They ask us to approximate 2.01. And so we're going to, in order to find essentially f of 2.01, it is approximately equal to, when you plug in 2.01 to your linear approximation, which is the 80 times 2.01 minus 2 plus 32. I mean, I could do really most of that in my head. 2.01 minus 2 is going to be 0.01. I know, it says calculator, so by all means. 80 times 0.01, 0.8 plus 32, which is going to be 32.2. Is that where I'm at?
No, 32.8.
Oh, it's a plus. I'm like, does it make sense if I say I'm adding and subtracting at the same time?
No.
Because I subtracted the 0.8, but then I left it at 32. Just, I screwed up.
Okay. Yeah.
Part of my brain added, part of my brain subtracted.
So if the answer is like terminating decimal, like that one where it's like 32.8, do we need to add 2 zeros to have 3 decimal places?
No, if it is precisely that answer, 1 decimal place is fine.
Add zeros, yeah. Because of significance.
I would say in science you start talking about significant figures. I started to say significant digits. I was like, that's not the right terminology. But no, to my knowledge, if it's only 32.8, that's fine. You don't have to add zeros. Okay, now use your calculator. So approximate. Here was the approximate. We approximate it to be 32.8. Okay. Use your calculator to find the accuracy. So if they're asking us to find accuracy, they're asking us to find the error. When they're talking about accuracy, they're talking about error. So when we start talking about error, I don't know why that word is so hard for me to say, but what is f of 2.01 minus the linearization at 2.01? So we know the linearization is that 32.8. I don't know, what is the 2.01 to the fifth?
32.8080401.
Okay, so 32.80804, gosh, BenQ kind of, something like that. You subtract those. We're getting
0.008.
Okay. 0.008 0401. Do I really need all these places? No. Okay. Now, with that in mind, that's our error, yes? If we express it like I talked about earlier, where your error is less than, what are we looking at?
10 to the negative second.
Yeah, there's 2 zeros here, so think of it as 10 to the negative second. So that is your error, okay? That is how accurate our approximation is. And then finally it asks if the linearization is an over or under estimate. When we start talking about over and under estimate, what do we have to know at that section? Not slope necessarily, concavity.
So
Okay.
plug it into.
Yeah, I would take a peek at the graph here. A graph just being x to the fifth. Okay. Now, it's pretty much a rather steep x to the third, yes? Okay. And actually, here, seriously, I want a little eraser. You give me a huge eraser. Okay. It's something like that. When we start looking at 2, okay, 2 is going to be somewhere over here, yes? And it's going to be the point 232. Where's our tangent line there?
It is.
What'd you say?
Outside to the right.
Yeah, like on the outside, like your tangent line is right here.
Yeah.
And I know it's hard to tell, but which way is our graph curving? It's concave up there. Okay, it's kind of hard to tell, but it's concave up. Officially, my tangent line is underneath it then, so it's an underestimate. Okay. And I know that one's a hard one to underestimate since curve is concave up, and tangent is below curve. I don't know how much of that you need to write, but write as much of it as you want. Okay. We're going to be pushing it here, aren't we? Yeesh. Okay. Didn't take us that whole time to do those three. Okay, moving along. 6. Is this getting repetitive? This one might be repetitive. Find the linear approximation to g of x equals the cube root of x at x equals 8. Use the linear approximation to approximate the value of the cube root of 10 and cube root of 16. Compare the approximate values to the exact values. Find the error of your approximation.
I say we skip it and come back a third time.
It actually, it's finding each of them. What are the others? We can do that. See where we're at with time at the end. Okay. We'll come back to 6. The thing is a lot of the same of what we were doing. It is for the most part. There is a slight, when you're comparing them, but it is, the basic directions are the same. However, have we talked about a table yet?
Yeah.
We haven't. Let f be a function that is differentiable for all real numbers. The table below gives the values of f of x and its derivative f of x for selected values in the interval -1 to 1. The function is concave up in this closed interval. Let me guess. There's a question about, C, is the approximation greater or less than? Okay, I already know the answer to that one. Okay, A, write an equation of the line tangent to the graph of f of x, where x equals -6/10. So they're wanting our linear approximation, yes?
Yeah.
So what we're saying here is that f of x is approximately equal to this linear approximation. Now, it said where x equals -6/10, yes? So all the information you need is right there. Okay, what goes first? Slope of -2. Parentheses. X minus
Plus
x minus -0.6, so it becomes plus 0.6, and then minus 51. Okay? So there's basically our tangent line. There's our linearization. Use this line to approximate the value of f of -5/10. I don't know about you guys, but I'm feeling like this is getting kind of repetitive already. What was the difference here? You were using a table. But if you're not intimidated by the table, this problem is one we already know how to do. So, f of -5/10 is going to be approximately equal to the linearization at -5/10, which is going to be -2 times -5/10 plus 6/10 minus 51. -2 times 1/10 minus 51. -0.2 minus 51. Is it -51.2, or did I mess up my math again? I got it this time. Okay. So linearization at -5/10 is -51.2. Yes? Okay, and that makes sense because it's close to -51, right? That's always kind of your okay, is it close? It makes sense. C, is this approximation greater or less than the actual value of f of -5/10, and give a reason?
Yes. Because it is below
We don't even have to sketch a picture or anything. We can sketch a picture based on the values they give me. But since f of x is known to be concave up on this interval, then the tangent line lies below the graph. And so your linear approximation is on that tangent line, and so it's below the value of the graph. Okay?
So concave up is underestimate and concave down is
Yeah, because like a concave up graph. So like, here's a section of concave up graph. Okay, kind of what I have sketched in my notes. If we're talking about this point here, there's your tangent line. Okay, there's your tangent line. So like, if that's where it's tangent and we're talking about, okay, this point over here versus this point here. So the idea that we found this at what? X equals -6/10, right? But they asked us to find it at -5/10. So the idea is the curve is your actual value. The tangent line is the linearization. So that's your linearization, the approximation at -5/10. Okay? So yeah, concave up will always have that. Since f of x is known to be concave up on the interval -1 less than or equal to x less than or equal to 1, tangent line lies below the curve, and the approximation is less than the actual value. Approximation is less than actual value. Okay. That was a quick one.
We got plenty of time.
Don't say that.
All right.
You know how that goes. We always think we have plenty of time, and then somehow, poof, we don't. Okay, 8. Write the linear approximation equation for f of x equals 1 over x minus 1 at x equals -1. Find an approximation for f of -1.2. Okay. So, is this the same thing we've been doing?
I feel like
It is. Could we possibly skip this one?
if you'd like
If
to
you
do
want
the other
to.
one more.
Well, here's the deal. 9 could be kind of good to talk about.
Let's just come back.
f of x equals 1 over x minus 1.
I mean, I'm just trying to,
-1 into x.
in all honesty, in comparison, 6 is probably better to go over than 8, as I, and I will tell you. So let's look at 9, and then we'll see where we're at with time. Okay? And what I will tell you is she will tell you, like, I always thought, like, oh my gosh, I have to do every single example. But she tells you, she's like, I put more examples in than what you need. But it's just hard to narrow them out, pick and choose. So, okay. 9. Given the implicit curve, x squared plus natural log of x over y equals 1. Write the linear approximation, linear approximation of the tangent line at x equals 1. Now, with this in mind, why is this a good one to talk about? And you're always saying, this is the same thing we've been doing. Well, it is, but the slope's going to be harder to find. Because notice it's a implicit curve. It's not solved for y equals, and it wouldn't be easy to solve for y equals. I'm not saying you couldn't. But, so, in order to find a linear approximation, we're going to need to find the slope, yes? options here. I'm going to rewrite this equation. What do you know about natural log of x over y? How could I rewrite that will make my life in taking derivatives easier?
X, Y,
That's
well, the natural log.
That doesn't really make
No,
it.
natural log of x minus natural log of y.
Because as it is right
the
now,
quotient.
as it is right now, that's the thing. You'd have to do the derivative of natural log of x over y. So that's 1 over x over y times the quotient rule of x over y. Yeah. Whereas here, if we catch it, we can just rewrite this as natural log of x minus natural log of y. That makes life a little bit better. Okay? Now let's take our derivatives. Remember, x's and y's are mixed, so it's implicit differentiation. Derivative of x squared is 2x. X terms, you don't have to write anything next to them. Plus derivative of natural log of x, 1 over x, minus derivative of natural log of y, 1 over y dy dx, equals derivative of 1?
0.
0. Solve this for dy dx.
I'm going to add over.
I'm going to say, yeah, 2x plus 1 over x is going to be equal to positive 1 over y dy dx. If it's 1 divided by y, can we just multiply by y over to the other side? So that's going to be y times the quantity, 2x plus 1 over x. Okay. I'm running out of room in this section. Yikes. This is my derivative. What do I need to know at the derivative? I need to know the slope, yes?
Oh, yeah.
The slope at when?
X.
X equals 1 now. There's a y here, so let's pause for a moment. We probably should figure out what the other part of the ordered pair is. Oh, hey. What's the ordered pair at 1?
1, 1.
How do we know 1, 1?
The graph tells us.
She gave it to us in the graph, yes?
What a nice lady.
I almost missed, I'll be honest, like, oh wait, we gotta go back and solve this, but. Okay, so we're gonna do dy dx evaluated at the ordered pair 1, 1. So 1 times 2 times 1 plus 1 over 1 so if your math matches mine, we have a slope of 3.
Yes.
Now, the whole point was to write the linear approximation, yes? So f of x is approximately equal to the linear approximation, which is 3 times x minus 1 and then plus 1, right? Okay, so that was a good one to talk about because I had to throw in that implicit differentiation that really never goes away. It's a skill that you're just expected to know at this point. Okay, B. Using the tangent line to the curve at x equals 1, so that's the linearization we just found, find the number k such that the point 1.25 is on the curve.
So we just plug in 1.25 for x.
Plug in 1.25 for x, and it's using the tangent line, yes? So we're plugging it into the linearization. So f of 1.25 is going to be approximately equal to the linearization at this point, 3 times 1.25 minus 1 plus 1. 3 times 0.25 plus 1. So K is 1.75. Okay. Calculate the error of the approximation.
After 1.25 so we plug it into the implicit curve equation. What did it block?
Wait, what?
Yeah.
I know I'm debating. Interesting. Okay. And so in order to do the error, you know you need to do the actual minus the approximation, yes? Now, the problem we're running into, okay, that was interesting. BenQ just did something. Approximation. The problem we run into, we have the approximation, yes? That's the L of 1.25. What we don't have is the actual. And I was just looking to see if there's an easy way. She didn't give us that information on the graph, did she? So I don't have that. Yeesh. So
What was it? I thought x squared plus.
Because there's an x over y.
it's not solved for
So
y.
do you have to solve it for y?
Yeah, essentially. Now, here, I'm going to go back to this line right here. Okay. We're going to solve it for y. So if I say, I'm going to isolate my y. So natural log of y, if I put that on one side. So if I add the natural log y over, are you good? Are you with me? And then on the other side, I'm going to have the x squared plus the natural log of x and the 1 you're going to subtract over. Are you guys okay with that? Okay. Now, okay, guys. We could have done this to take the derivative earlier, but it wouldn't have been any easier. What do you guys remember here? Natural logs have base.
10.
No.
E, sorry, that's
E. LOG, log, has base 10. Natural log has base E. How do you go out of log form into exponential form? Left, right, middle. Okay, left, right, middle. So what are we going to say here? The E on the left raised to the junk on the right, x squared plus natural log of x minus 1 equals, what's in the middle? Y. So we just came up with the equation y equals e to the x squared plus natural log of x minus 1. It's there, isn't it?
Yeah.
Now, can you plug in 1.25? Okay, it's definitely a calculator. What'd you get?
2.19381.832. Is that all you got?
I have 2.19382 written down in my notes, so that's the shortened version of yours, right? Tate hit a wrong button.
Yeah. Oh my gosh. I went to the exponent of 1.25, and I put the rest of the equation in the 1.25.
Okay. So we're going to be using, let's see, the 2.19 and the 1.75, more than 2.19, but you know what I mean, to subtract and find our error. What are we getting with our error?
0.4438.
Yeah. I have 0.44381 written down. Now, okay, I have that there. What I want to take a moment to say here, and I don't quite have room to write down there below. Okay, that's our error. We could say it's less than 10 to the 0, right? But what I never asked us to do here, and I think I put it in on my own because they never asked us to find the percent error. Although you probably have a pretty good idea of how to find percent error.
Yeah, isn't it just that over the exact?
And then multiplying by 100. So again, it's just they never asked us to find the percent error. So you might want to put this, I'm running out of room at the bottom, but just so you're prepared for homework, that it's going to be officially the absolute value of the f of 1.25 minus the approximation at 1.25 divided by, as Caitlin said, the original, the actual, and then officially times 100. That just makes it the percent form.
It's kind of a big error.
And what do you get?
20.234.
Yeah. I have written down 20.230% as the percent error. And again, it didn't ask us, but I don't think we ever saw percent error in the notes, so I wanted to make sure that we talked about that. Okay. And now keep in mind, the error of approximation doesn't have any zeros in the decimal, does it? It starts off 0.44 instead of 0.00. So that should tell you my error is going to be kind of big. You know, usually we're within decimals, and this is, I guess, within decimals, but not what I think of within decimals. Okay? Look at the time. Tell me, where'd the time go? Okay.
That's what I thought.
Huh?
There's a song.
Okay. Well, we skipped 6 and 8, but in all honesty,
6 looks harder than 8, but still.
but even then, it's still a lot of the same.
Yeah.
So, as always, if you need to go back and look at 6 or 8, they are in your notes, which I'll check. I need to check, make sure I ain't posted the answer keys. But they are there. Okay? So, 4.5 homework for tomorrow. And we'll start talking about L'Hopital tomorrow.